7.11 deals with predicting the products of a reaction and determining whether substitution or elimination will predominate. And by now it should be clear that a number of factors affect the products formed when reacting an alkyl halide with a nucleophile and a base or a base. The substrate, the reagent, the solvent, all of these things have to be taken into account when we're deciding which products will be formed. It also says it should also be clear that in many cases a mixture of substitution and or elimination products will be obtained. So here's an example of a secondary alkyl halide. We're treating that with a strong base and a strong nucleophile, and you can see that the elimination products predominate and that I also get some of the substitution product. And then between the two elimination products, you can see that the Zaitsev product, or the more substituted alkene, that is the predominant of the two alkenes, the more substituted alkene. So you need to be able to look at a substrate and decide what's going to happen. So here's an example where only one product is formed. So it says here for this substrate, only one mechanism will occur. So we take this compound, this is tert-butyl iodide. I treat that with sodium methoxide. So this is, we can write that in here. This is called sodium methoxide. And the OMe, that stands for O-methyl. And this is the conjugate base of methanol. So this is a strong base and a strong nucleophile, but it's not going to behave as a nucleophile with a tertiary alkyl halide, so we'll only see the elimination product. So you could practice drawing the mechanism. So if I redraw my methoxide, so I could practice drawing the abstraction of this proton and forming the double bond like that. So in order to understand how to use these reactions to transform alkyl halides into a desired compound, you should be able to predict all the products that will form in a given reaction, as well as the major and the minor products. So it's going to be a lot of work. So what do we have to do? It says to successfully predict the products formed in given reactions, we can follow this three-step analysis. So I don't really have three steps here, do I? So step one is going to be determine the function of the reagent. So is it a strong or weak base? Is it a strong or weak nucleophile? Then you're going to analyze the substrate and determine the expected mechanism. So you'll ask yourself, is this primary or secondary or tertiary, or is it benzylic, right? We looked at benzylic, or is it allylic? So those will be the factors to consider. And number three, it says consider any relevant regiochemical and stereochemical requirements. So we'll have to take those into account too when we're evaluating what products will be formed. So function of the reagent. So what kind of reagent are we dealing with? Well, if we're dealing with a strong nucleophile, nucleophiles generally promote substitution reactions. So a strong nucleophile will promote an SN2 reaction, whereas a weak nucleophile, generally speaking, will promote an SN1 reaction. And then when we see an E2 reaction, generally speaking, this is with a strong base, and an E1, that will predominate when we're dealing with weak bases. So the following table is a good resource for categorizing reagents and the mechanisms that they will promote. So this is in your textbook. This is figure 7.19, and I think it's a great idea to memorize this table. So I'll even write down here, memorize this table. So you should know in the first category here of E2 promoting reagents, so it says a strong base and weak nucleophile. So the first one, NaH, so this is sodium hydride. So if you want to draw out the Lewis structure of hydride, you should know what that is. So you can see that hydride will be a good base because it's the conjugate base of a very weak acid, H2. And then these two here, DBN and DBU, I'll talk about those in a few minutes. So if we move over to the next one, so strong base and strong nucleophile. So you can see that these are oxides like hydroxide, methoxide, and ethoxide, which are the conjugate bases of water, methanol, and ethanol, respectively. Moving on to the next category here. So it says here weak bases, but strong nucleophiles. So I have iodide, bromide, chloride. This one here, this is called a thiolate. So that's the conjugate base of a thiol. Then this one here, this is a thiol. Then I have hydrogen sulfide, and the conjugate base of hydrogen sulfide is called hydrosulfide. And you can see why the ones with the negative charges would be good nucleophiles, because they have negative charges, so they'll be attracted to nuclei. Whereas the thiol and the hydrogen sulfide, well, sulfur is a very polarizable atom, and we discussed how nucleophilicity is not just a matter of charge, but it's also a matter of the polarizability of an atom. And then finally, for the last one, we have weak bases and weak nucleophiles. So those will be things like water and alcohol. So we have water and then methanol and ethanol. So again, it's a good idea to memorize this table so that when you see one of these reagents, you'll know which pathway, which mechanisms will predominate. So a little bit more about these bases that were in the E2 category of figure 7.19. So you remember there was sodium hydride and these two other bases that are strong bases but weak nucleophiles, and sometimes we call a weak nucleophile, we'll call them non-nucleophilic bases. So if it's non-nucleophilic, it means it doesn't behave as a nucleophile. So the first one, DBU, and these have really long names. So this is 1,5-diazobicyclo-430 non-5-ene or 5-nonene. So we call that DBN, and the other one has a long name which I won't get into, and that's DBU. But anyhow, if you look at what happens when if either of these, DBU or DBN, if they were to take on a proton or become protonated, that you can see that the positive charge would be resonance stabilized. And it's shown here for DBN, but you should be able to draw the same type of protonated species, and you should be able to draw the resonance contributor with DBU as well. But you can see how if that positive charge is resonance stabilized, DBU and DBN will make really good bases. And it's kind of interesting because these are strong bases, but they don't have a negative charge. So this is something a little bit new for us. Also, you can probably guess why they're non-nucleophilic. I mean, they're so sterically hindered that there's no way that these could behave as nucleophiles. So this is probably the most important figure in the entire chapter, and this is figure 7.20. This is in our textbook, and the textbook says something to the effect of you must have a strong command of this table. You must memorize this table. You must memorize this table. But the thing is if you memorize this table and then you try all of the practice problems in the book, you will develop a very strong command of this this figure, of figure 7.20. So for the strong base and weak nucleophile, so those are things like sodium hydride, DBU, and DBN. And then for the strong base, strong nucleophile, those were things like hydroxide, methoxide, and ethoxide. And then for the weak base, strong nucleophile, there were 7 of them listed in figure 7.19. So I have iodide, bromide, chloride, which were all pretty big and polarizable anions. Then I have RS minus, again, that's called the thiolate. I have HS minus. I also have RSH, which is a thiol, and then of course I have hydrogen sulfide, because sulfur is just such a big and polarizable atom. And then the last category is weak bases and weak nucleophiles. So that would be things like water, methanol, and ethanol. I would recommend printing this slide out at the very least and trying to memorize that. Anyhow, so I'm going to refer to figure 7.20 quite a bit from now on and in the videos to come. So let's keep moving here. So a little bit more about regioselectivity and stereoselectivity. So after you've taken a look at the reagent and the substrate, you can say which mechanism will occur using figure 7.20. You can use that figure to help you predict what the products will be. Then, once you know, okay, I'm going to have an SN1 reaction or an E2 reaction or whatever, then you're going to draw all the possible regioisomers, stereoisomers, then choose the major and minor products using the guidelines that we've learned. So for an SN2 reaction, you're going to observe a single product, and that product will involve inversion of configuration at the alpha carbon if it is a chiral center. So it says down here the nucleophile attacks the alpha position, and we discussed what an alpha position is, where the leaving group is connected. So again, the inversion of configuration, that's just like an umbrella flipping in the wind. So for E2 reactions, we're going to draw all the possible alkene isomers because E2 is an elimination reaction that produces alkenes. Only alkenes which result from a beta hydrogen antiperiplanar to the leaving group can form. So if we use a bulky base, so a good example of a bulky base, let me see here. There we go. So a good example of a bulky base would be something like potassium T-butoxide. So if I write this out, T-butoxide, like that. Then we're going to get the Hoffman product as the major product. If a non-bulky base is used, so these would be things like hydroxide, right, methoxide, ethoxide. Then generally speaking, I'm going to produce the Zaitsev alkene as the major product. Also, I'll just add this here. It says the process is stereoselective because, when applicable, the trans disubstituted alkene is going to be favored over a cis, and we discussed that earlier on. So the process is also stereospecific. So when I only have one beta proton, so it says here when the beta position of the substrate has only one proton, the product that I'm going to form is going to result from the anti-periplanar elimination. So in that case, I'm going to have to draw a Newman projection. For an SN1 reaction, we draw the carbocation intermediate and we consider if it will rearrange. If it doesn't, well, we just attach the nucleophile to it. If it rearranges, then we're going to draw the product of either the hydride shift or the methyl shift. And then that chiral carbon that's formed by attack of the nucleophile, I will get two products. I'll get either I will get R and S because it's proceeding through a trigonal planar intermediate. All right. And then lastly, for E1, you're going to draw the carbocation formed after the leaving group leaves. And if it rearranges, you're going to draw the rearranged carbocation, just like in an SN1 reaction. Then you draw all possible alkene isomers that result from beta hydrogen abstraction. So all possible alkene stereoisomers will form, but I can't choose which isomer I want by choice of base, so like I could with an E2. So the major product is always going to be the most stable alkene in this case. Anyhow, there we go. So if we take a look at an example, it says predict the products for the following reaction. So I have this this chiral compound. I have sodium hydroxide. So if I draw the structure of sodium hydroxide, so I have Na plus and OH minus, and I could put in my lone pairs here. Oops, I'm missing an electron. So there we go. So hydroxide is a strong base, and it's a strong nucleophile, and I have a secondary alkyl halide. So if I go back to figure 7.20, it says that when I have a secondary alkyl halide and a strong base and strong nucleophile, that E2 is going to be the favored mechanism, but I will get some SN2 product. So there we go. So moving on from there, so if I first start by drawing the SN2 product, well, it proceeds by a backside attack, and therefore I get inversion of configuration. And it's always a good idea to practice drawing your mechanisms. So if we draw the hydroxide, we have our nucleophilic attack like this, and our loss of leaving group simultaneously because it's SN together. It's a concerted process. So there we go. So I get my SN2 product, and then of course we don't include the sodium bromide, but if you want to balance out the equation, you would end up with sodium bromide as well. No need to draw that, but it's just kind of fun to put it in sometimes. Then as far as the E2 product is concerned, well, you can see that I have a few different types of beta hydrogens. A few different types of beta hydrogens that could be anti-periplanar to the leaving group, and you could practice drawing the Newman projection for all of these elimination products. So in this case, I'm going to end up with this product here, which is from the elimination of one of the HC protons. So that's the Hoffman product. And then I have two disubstituted alkenes, the first one and the second one here. But then this one is going to be the major. This is going to be the major product because this is the least hindered alkene product. So in this case, this is the E product, or You could call this trans as well because the two protons are trans to each other. These ones are cis to each other. So you could call that Z or cis. But this will be the major product. So in this case, this would be a perfect example of where you really have to be on your toes when you look at a question like this. So you have to answer the question with the substrate. So you say this is a secondary alkyl halide. It has a chiral center. What kind of reagent am I using? I'm using hydroxide, which is a strong base, a strong nucleophile. When it comes to alkenes, I have two types of disubstituted alkenes that I can form. This one being the major because it's the least hindered. I also form the Hoffman product, and I also form the SN2 product, which this isn't even the right product. So let's draw that in. So if we fix this up, so this would be the SN2 product like that. There, that's fixed. So I hope you find this video helpful, and we'll take a look at this question in a future video.